time complexity, where we'll be looking at the quick sort. Now, the quick sort operates on the O n log n, which is the linearithmic time complexity. Remember in the previous video, we looked at the mesh sort. So here we're going to be looking at how quick sort works, right? Now, assuming that we have a variable, so let me use the same variable we used for the mesh sorts. Let me use the same list, sorry. Let me use the same list we use for the mesh sort, and let's use it for the quick sort here. So now, we have an unsorted list of 4, 2, 0, and 1, right, for the quicksort. And we are told to use quicksort to sort these items in this list. Now we have a variable called n that holds this list, which is 4, 2, 0, 1, and we are told to use quicksort. So what it does is this. Now, the quicksort chooses a pivot, choose a number here within this list as a pivot. Now let's assume that our first item located in the first index is our pivot, right? Let's assume that our pivot is the first item, which is 4, right? Which is 4. So now what happens is the quick sort will divide this list into two halves, which is the left and the right, right? So now what it does is it doesn't do it just like the way we did it here in the mesh sort of divide by two. So here the division is based on the pivot we picked. So in the left hand here, in the left here, every number, right? Every number after the number located in the first index, every number here less than 4 goes to the left, and every number greater than 4 goes to the right. So in this case here, we have a list here which have the 2, 0, and 1. Now, these numbers are less than 4. So it means that the right has no number greater than 4. So now we are working with the left now. There's no number in the right hand side. So that means no pivot will be performed here because no items is here, right? So now in this case here, we'll perform recursion here and we keep on dividing things until we have a separate item which is less than or equal to 1 here. Now for the left hand side again, we'll pick another pivot. Remember, the rule states that our first index should be our pivot. So our new pivot here will be 2, right? So now in this place we have another left and we have another right, right? So our new pivot here is 2. So in the left hand side, it means that 0 is less than 2 and 1 is also less than 2, which means this right is nothing. So that is how we keep on doing this. Here we pick a pivot here, which the pivot here is what? Is 0, right? This pivot here is 0, and 0 is our left hand here is what? Is there's nothing because 1 is not less than this. Then our right hand here becomes what? Our 1, right? Now you can see in the process of doing this pivot, you can see that this is actually, they are all sorted, right? They are all sorted. Now let's do it in a way that we'll all understand this. Let me make this a single list. Let me make this a single list. Okay, let me use this. So this is quick sort. This is quick sort O and N. So now let's use this so that we understand how it's done. Right? So we have our N here. So equal to, let me copy this. Okay. So let me just paste it here so that we understand it better. So we have our N now. So let's do this. So in the first instance here, our pivot is, so pivot will be at the middle. Our pivot is 4, right? Which we pick the first one here. Then all the numbers lesser than 4 goes to the left, which is 2, 0, and 1, right? 2, 0, and 1. And the right, nothing, there's no items in the right because we don't have any number greater than 4. Now, we keep on dividing this. Recursively, we keep on dividing this. So our next line here, right? Let me put it here like this. So our next line here, we'll pick another pivot, which is what? Our pivot, which is 2. Remember, we're working on the first place here, which is 2, right? So now every item less than 2 goes to the right, which is 0, goes to the left, which is 0 and 1, right? You can see then this one, there is no item. So let's leave it as blank. Let's leave this as blank, right? So now we have two items here in a list, which we still divide them. This is 1, this is less than equal to 1, this is less than equal to 1. So nothing happens, no recursion happens here, but there's a recursion that will happen here because we have more than one item here. So now in the next line here, we pick another pivot, which 0 is our pivot, right? 0 is our pivot, and then 1 goes to the right. Now, looking at this now, you can see that the items are already sorted, right? You can see that the items are already sorted. Now, we can see that we have 0, 1, 2, and 4, which is equal to 0, 1, 2, and 4. Now, you can see that this is faster than the merge sort because in the process of dividing this, it's automatically sorting it, right? So it performs divide and conquer, which is logarithm time complexity, and also perform the linear time complexity alongside with it. So you can see how fast this is, right? You can see that we picked a pivot here. Look at the first one, pick a pivot which is 4, and every item less than 4 goes to the left, which is this, which we have 2, 0, 1, right, and 4. Now there's no item in the right, so we can leave it blank. Now you can see that this item here is less than one item, right? So that means recursion will be performed here, right? Recursion will be performed here. So that's why we picked. Remember, we are performing a rule to pick the first index, the first item located in the first index as our pivot. And now 2 becomes our new pivot here. And then every item less than 2 goes to the left, which will now have 0, 1, 2, 4, right? So now we have another one. We have a list which is not greater than 1, which is this. Recursion will not perform here because the item here is equal to 1. Recursion will not perform here because the item here is equal to 1. But recursion will perform here because the item here is greater than 1. So that's why we pick another pivot, which is 0, and this becomes our pivot. And then we're left with 1. Now 1 is greater than 0, so it comes to the right. So you can see that automatically this is sorted. That is how the quick sort works. You can see how simple it is. Now the next thing to do, right, is write an algorithm, right? Is to write an algorithm for these quick sorts, right? To write an instruction for this quick sort and how the computer will perform this quick sort, right? How the computer can be able to sort these items using this quick sort. Now you can see that this operation operates on on a linearithmic time complexity, which is a combination of the linear time complexity plus the logarithm time complexity. Now let's write the algorithm, right? So now we have a function, we have a function called quicksort. Now this function will have a parameter which is an array, right? So now the first thing you need to do here is to find out now if the length of the array is less than or equal to 1, right? So what happens? We need to return back the array. We need to return the array. Now the essence of this is that you can see this function here will work on a constant time complexity if there's only one item in this list. So this works in a constant time complexity. So this, in the best case scenario, right, when this instruction is given and when we have just one item here, this will just return just the item which work on a constant time complexity. But in the average case or the worst case scenario, where there are more than one item, everything here works on this linear arithmetic time complexity because the operation after this will be performed, right? So now we have understood this if length of array less than equal to 1, so return the array, right? Then we have a variable called the left that will hold the items in the left hand side. Then we have a variable called right, which is a list, right? This is a list which will hold the item. For now they are empty, right? Now we'll pick a pivot. So our pivot becomes our first index, right? Becomes the item located in our first index, and to get it is to grab the array and then we put 0 here, which picks the item located in our first index, right? Now we'll perform a linear time complexity. We'll have a loop where we have for I, right, which is variable for I equal to 0 down to the length of n. Now we would start I equal to 0 because the pivot is already picking I equal to 0 here. So let's use from I equal to 1, right? Which we have explained this. If you don't understand how this works, you can look at the previous lessons so you can understand this iteration, you can understand these loops, right? Now for I equal to 1, which means the iteration started from 1, right? Started from 1, which means I equal to, because we have the length is n, right? The length of n is 1, 2, 3, 4, which means it performs 4 iteration here. But because we are starting I equal to 1, automatically this will go 3 times, right? So for I equal to 1, where we now have, so I will make my comparison. If the array of I, right, is less than our pivot, right, is less than our pivot, so what happens? I want it to take then left, which is this left, append the item to the left hand side, which is left dot append, right? Now take the item to the left hand side, right? Then else, else take the item to the right hand side. Take the item to the right hand side, right? So you can see what happens, right? So now the next thing to do here, right? Well, the next thing to do here is we have picked a pivot which is 4. Every item less than 4 goes to the left, which we have done here, and every item greater than 4 goes to the right, right? Goes to the right. So at the end here, we'll perform recursion until then. At the end here, we are recursively calling this function here. We'll call the function, we're returning the quicksort. Remember the quicksort have a parameter, so we're passing the argument, the quicksort, which is the left, plus our pivot, plus our pivot, plus our quicksort again, which we call the right. Now, this is the algorithm. Let me just make this better. So this comes here, this comes here, right? This comes here. Okay. Now, this is the algorithm for quicksort, right? So we have explained this. You can see what happens here, right? Now, we have explained this where we have 4, 2, 0, and 1. But we have 4, 2, 0, 1. Now, in the first instance here, this is false, so it goes to the next one here. It's false because we have more than one item here, right? So it performs this. So we have a left hand side, which is an empty list. We have a right hand, which is an empty list. And then we have a pivot, which picks the first item in this list here, right? In this list here. Now, what happens here is for I in 1, which means that I equal to 1, I equal to 2, and then I equal to 3. So we are skipping I equal to 0 because we are starting I equal to 1, right? So it automatically is to perform 3 iterations instead of 4. Now when I equal to 1, it means that I equal to 1 is there is this 2 is located in index 1, right? So if 2 is less than the pivot, which the pivot in this case is 4. Now 2 is less than the pivot, right? Since 2 is less than the pivot, it goes to the left hand side, which we explained earlier. You can see 0 is also, it goes down to the next iteration. It goes down to the next iteration, which is 0. 0 is less than the pivot, which goes to the left. It goes down to the next iteration. 1. 1 is less than the pivot, which goes to the left. Now you can see what happens, right? Now that is how it keeps on doing this recursively, right? So that is it. Guy keeps on doing it recursively because when we call this function quicksort and we call this left, right? So it goes back again here because this left is more than 1. That is how it keeps on doing it until we have a separate list plus our pivot, which we are picking here, right? Because the pivot is always picking the first index plus the pivot plus the quicksort, just like the way we explain how the working does. So that is what this recursion will do until everything is sorted, right? So if we are calling this function, right? If we are calling this function, if we pass this end to this end as the argument here, it will automatically solve this. Just like if we are printing, if we're output output this function I will call output quicksort, right? Then you pass this argument n as the array. Remember, we have a parameter array here within this function. So if you are passing this automatically, it will sort this based on this algorithm here. You can see that quicksort is actually simple more than merge sort, right? So if you have any question, feel free to ask me. I'm always here to answer you. So in the next video, we're going to be looking at the logarithm time complexity, where we'll just use one example, right? But in the classroom, we're going to be showcasing different examples of the logarithm time complexities and also other time complexities. I hope you understand this video. Thank you and God bless you.